Welcome to example number 9. We have a roller coaster here that is traveling along this path A, B to C. And we say just as it gets to the top, it just barely stops and then continues to going down to part C. And we're asked to find out how fast it's moving at point A and at point C. Let's go to a simulation to help you understand this. All right, I pulled up this energy skate park simulation to help you visualize what's happening in the problem. So just imagine that the skateboarder is basically a roller coaster. This is the flat part, position A, the top of the hill where the roller coaster barely stops, and then as he goes down the hill, the final spot is point C. And I've also provided an energy bar graph to help you visualize what's happening with the transformations of energies. Okay, so just take you can look at the energy chart too and watch him as he goes along here. So here, press play. So now he's being released. He's gaining kinetic energy, and now he's losing potential energy. Gravitational energy is increasing, just comes to a halt, and then he starts going down that hill and starts gaining kinetic energy and losing gravitational potential energy. So I'll just stop him here, right here, and hopefully that gives you an idea what's happening to the energy transformations. So in this case, I'm going to consider the roller coaster and the Earth as being my system. Remember, I've shown it over here with the system being in this circle. And then I've also shown energy bar graphs here from A, B, and C. So go ahead and I guess the first thing I would do besides after doing the system and putting these energy bar graphs is I would choose an appropriate reference level for your gravitational potential energy to be 0. So where would you like your y to be equal to 0 in your diagram? Personally, I choose this point here, C, to be the reference level. It's really up to you, but I like to have all of my gravitational energies be positive. So this point, I'm going to say, is 0. So essentially, y at position C is 0. Y at C is 0. Y at B would be 15 meters plus 10 meters, which is 25 meters. And the y at position A would be this distance right here, which would be only 15 meters. So the next thing I would do is then start to put in our bar graphs in here. I'm going to choose to go to part B first, this position B here, because I know when it gets to B, it's not moving at all. And if it's not moving, it doesn't have any kinetic energy. It's all gravitational energy. So I'm going to put over here a nice big long tall bar here, which represents the gravitational potential energy. And then let's take a look at position A. I have both gravitational energy and it's also moving to the right. So I'm going to draw in a slightly lower gravitational potential energy, maybe about 3/5 the height, and then a little bit of kinetic energy, about 2/5 of that height here. And so I've decided to put in like 5 blocks here and say, let's say 3 blocks here and 2 blocks. So you can see that the total we have is 5 blocks here and still 5 blocks here. And then when I get to point C, where that reference level has no more gravitational energy because its height is 0, then I'm going to have entirely kinetic energy. Now, it may help to put down what you know at each position. Let's put these things over here. So I know all these vertical heights. I also know that the speed at B is 0 meters per second. I do not know the speed at C, nor do I know the speed at A. I also know constants like G is 9.8 newtons per kilogram or meters per second. And that's going to be helpful as well. So now we can proceed to write our energy statement based on our bar charts in our system. You may notice, by the way, I left out thermal energy. And I'm making the big assumption that this, well, it says frictionless. If it had friction, then I'd have to include the work done by friction. But let's make the assumption there's no thermal energy lost due to friction. And so really, the mechanical energy of the system remains constant. So if we write our energy statement, we could say that the energy at position A would be equal to the energy at position B, which is also equal to the energy at position C. And if you look at our bar chart, we have the kinetic energy at A plus the gravitational potential energy at A. And then if you look at the energy at position B, we just have gravitational potential energy at B. And then if we look at the picture C, we have just we have kinetic energy. That's it at position C. There is no gravitational energy. And so really at this point, now you can substitute in formulas. You have 1/2 m velocity a squared plus you have mg h sub a, and that's equal to the gravitational energy at B, which is mgh at B, and that's equal to the kinetic energy at C, which is 1/2 m velocity at C squared. And you may notice that they all have the same mass. The roller coaster's mass doesn't change here, right? So the masses actually all cancel out. It's irrelevant, actually. And so you could reduce the statement to 1/2 VA squared plus G times HA equals G times HB, which is also equal to 1/2 VC squared. So now it's just a matter of solving it. If you're trying to solve for the velocity at point A, then you would be looking for this velocity. And if you look at your known information, oh, by the way, I've been using H's. I'm just so used to H's because that's the old way the formula was written for me when I learned it. Actually, it should be Y's based on the AP formula sheet. So let's change that to Y sub A and Y sub B. And over here, Y sub A and Y sub B. So if we're solving for that velocity at position A, we're really just going to use this part right in here. So let's just put that over here, part A. We have 1/2 velocity A squared plus G times Y sub A. And that's equal to G times Y sub B. And now we could substitute in. We have G is 9.8, Y sub A is 15 meters. And G is 9.8, and Y at B is 25 meters. And so then we just go ahead and solve it. Turns out it's the square root of 196 meters squared over second squared, and that would give you a speed of exactly 14 meters per second. If you're solving part B, which is the velocity at C, I guess we could just use this section right here. We'll just go right underneath here. G is 9.8. Y at B is 25 meters, equals 1/2 the velocity at C squared. And the velocity at C would be the square root of 490 meters squared over second squared, which is approximately 22.1 meters per second. Okay, and that's it for this problem.